Hello everyone, this is 6.1 and this is the table method, an intro to what is called the Simplex method. And basically what we'll be discussing in this section is an extension of what we saw from 5.3 when it came to linear programming. So first, let's recall what linear programming problems were. Problems where you have to maximize a certain objective function given certain constraints, so subject to these certain constraints. And what we're going to discuss in this section is what is called a standard maximum problem in standard form. It's kind of a mouthful, but it's basically something that looks like this. So here, this is our objective function we're given. These are our constraints. And then we have non-negative constraints as well. So to be in standard form, or for it to be a standard maximization problem in standard form, let me just say the following. So a standard maximization problem in standard form, again it's a mouthful, must have the following. It must have an objective function that is written like this in standard form. So it must have p is equal to something times x1 plus something times x2 and so on. And I say x1 and x2 because there could be more. There could be x3 and x4 all the way to xn. But that's what I'm going to say there. And our constraints, so this is our objective function. Now as far as our constraints go, they have to be of this form. So the constraints have to be of the form less than a positive number. So it can be something times x1 plus something. I don't want to use a and b because I already use a and b here. Let's just say cx1 plus dx2 plus dot dot dot, because again there could be more than one. And there could be more than one constraint, so like here there are two constraints. And then in addition to that we have to have our non-negative constraints as well. All of our variables x1, x2 and so on are each all bigger than 0. So something like this example is in what is called standard form, but more specifically it's a standard maximization problem in standard form. So it's a certain type of problem we'll be looking at, where we want to maximize a function, because in 5.3 we saw we can maximize and minimize. We also saw that constraints could be different, they don't have to be less than completely, but for a standard maximization problem in standard form, they do have to be less than. So that's basically what I'm discussing here, and those are the only kinds of problems we're going to see in this section. Alright, so the next thing I want to take a look at are the constraints we had. Not the non-negative constraints, but the actual inequality constraints I was talking about earlier. And this is what is called an inequality system, or I system. So I system just means system of inequalities. Opposed to E system is an equation system, so it's a system of equations opposed to inequalities. So here there are less thans, or possibly greater thans, but for these problems we'll be seeing in this section, it'll always be less than. And here there are equal to. Now the question is, how can I turn an I system into an E system? I mean, one way to think of it is that you can just imagine that it's equal, and that's fine. But to legitimately make it an E system, well, this quantity here, x1 plus 2x2, is just some number. Depending on what x1 and x2 are, the value will be a number, and that number has to be less than 32. So I hope you agree, if you add some random number to it, you can get 32. Maybe not a random number, but there exists a number you can add to that quantity to make 32. So just as an example, let's imagine we have x1 and x2 values that make x1 plus 2x2 25. 25 is certainly less than 32. But what must you add to that quantity 25 to make it 32? In this case, 25 plus 7 would be 32, but I'm just trying to say that that's something we can always do. It may not always be a clean number, but regardless, there's a number that you can add to that to make it an equality. So the numbers I'm going to use here, or the letters I'm going to use anyways, are S1 and S2, and these are what are known as slack variables. And the reason why they're called slack variables is because they're, I guess, considering the amount of slack you need to add that 25 in that example I gave to make it 32. So there's a number you can add to that to kind of fill in the slack, so to speak. The next thing I want to take a look at now is the feasible region of our constraints, and we'll see the slack variables in this E system taking a role there. But for right now, let's see how we do this. Remember, we create the lines by considering x and y intercepts. In this case, it's the x1 and x2 axes, because it's not x and y technically, but that's fine. You can just imagine they're x and y, I guess, but just to be specific, it's x1, x2. So for the x1 intercept, you set x2 equal to 0, so that means it's going to be 32. For the x2 intercept, set x1 equal to 0, divide by 2 to get x1 or x2 by itself. 32 divided by 2 is 16. Connecting these gives us this line. Good. For the next one, we'd have to divide by 3 to get x1 by itself, assuming x2 is 0 for the x1 intercept. So 84 divided by 3 is 28, so that's going to be way up here. 28 is the x1 value, so it's actually going to be over here. So let's say that's 28. There we go, that's what I meant to say. For the x2 value, if you divide by 4, 84 divided by 4 was 21. Perfect. And we have a point of intersection here. Also, since they're both less than, we shade below the lines. Remember, since we have non-negative constraints, we're in the first quadrant. So this is our feasible region. Now, a very, very, very important consequence here is that the slack variables will be positive numbers. This should make a lot of sense. Consider that problem I gave you earlier. I said if this number, if x1 plus 2x2 amounted to 25, s1 would have to be 7. But what if, what would make s1 negative? Well, what if these numbers, let me just circle it, what if instead of amounting to 25, they amount to, I don't know, 40? If they amount to 40, then s1 would have to be negative 8. But do you see the problem there? The problem there is that if x1 plus x2 was equal to 40, well, 40 is not less than 32. And we need to be less than 32 in order to be in the feasible region. So if s1 or s2 are negative numbers, then those x1 and x2 values will be outside of the feasible region. So we only consider s1 and s2 to be positive. An important consequence here is that the slack variables must be positive in order for solutions to be in the feasible region. Otherwise, like we saw earlier, if they were negative, that would imply that the solutions to x1 and x2 in this case would not be less than this number, and the solutions would be outside of the feasible region. So that's something to keep in mind. Just say though, before moving on, we want to consider the corner points of this feasible region, and there are 4 of them in this case. There is 0, 0, there is 0, 16, 28, 0, and then this one, which required a lot of work, if you recall, from 5.3, we would actually have to solve the system. x1 plus 2x2 is equal to 32, 3x1 plus 4x2 is equal to 84. Okay, now what we're going to do is I'm going to show you exactly what the table method is. I'm going to basically cut to the chase and explain how these slack variables come into play and how we can essentially solve this type of problem without graphing. Alright, so like I was saying, I want to show this table method, and it involves a non-graphical approach. So everything I showed you just now involving that feasible region, you can keep in the back of your mind, but we wouldn't know that if we were trying the table method. If we wanted to do the graphing method, then yeah, you can find the corner points like that. But otherwise, how do you find the corner points? Well, here's what you do. You set each of these values equal to 0, essentially one at a time. Except for the fact that the non-negative constraints basically allow x1 and x2 to be 0 right away. So it is a possibility that x1 and x2 are 0. Now, if x1 and x2 are 0, we need to see what s1 and s2 would have to be in our E system. So notice, when x1 and x2 are 0 for the first equation, we get s1 is equal to 32. Similarly, when x1 and x2 are equal to 0 for the second equation in the E system, we get s2 is equal to 80. It should have been at 84 this whole time. That was my mistake. So it should be 84. All right, good. Now what? Well, now what we want to essentially do is find the x1 and x2 intercepts for each of these equations. So what I'm going to do is in each of these equations in the E system, I'm going to let everything be 0 essentially except for one of the x1 or x2 values. So let me let x1 be our first non-zero in the first equation, meaning I'm going to let x2 and s1 be 0. So if x2 and s1 are 0, what does x1 have to be? Well, if those are 0, x1 has to be 32. This will correspond to that corner point 32, 0. Well, it wasn't a corner point, but it was an x-intercept. It was an x1 intercept on the line, and that's what this corresponds to. Now, when you have these points, though, or these values for x1 and x2, and you plug them in here, what does s2 have to be now? Well, think of it like this. So plug these in. If you plug these in, you get 3 times 32, which is 96, by the way, plus 0 times 4 for 4x2, that's 0, plus s2 is equal to 84. So that means if you were to actually find s2 by subtracting, you would get s2 is equal to negative 12. This is not good. Why is it not good? It is not good because s2 and s1 we want to be positive. Otherwise, that means our solution is not in the feasible region. What this basically says is that 32, 0 is not in the feasible region. And if you look back, it wasn't. So, moving on. Now, instead of letting x1 be our non-zero value for the first equation, let's let x2 be our non-zero value. So that means x1 and s2 are going to be 0. Okay. So if s1 and x2 are 0, then that means x2 has to be 32 divided by 2. So if those are gone, then you get 2x2 is equal to 32 divided by 2, x2 is 16. Okay. And now plugging these into the next equation to find s2, because we want to fill out each row of this table going down. If x1 is 0 and x2 is 16, then in the second equation we get the following. We get 0 plus 4 times 16 is 64. So that's 0 plus 64 plus s2 is equal to 84. Subtracting 64 gives us s2 is 20. And that's positive, so that's good. So I'm not going to put a sad face there. And I want to do the same thing for the, well, let's see. Yeah, so now I want to do the same thing for equation 2 now. Because this right here, these were basically just the x1 and x2 intercepts for the first equation. But now for the second equation, we're going to play the same game. For the second equation, if we only want x1, imagine these are 0. x1 is going to be 84 divided by 3. 84 divided by 3 is 28. And again, x2 and s2 are 0 in that case. And if we plug x1 and x2 into the first equation to find out what s1 is, because we need s1 now, and s1 is in the first equation, well, 28 plus 0 times 2 is going to give me 28 plus 0 plus s1 is equal to 32. So subtracting 28, we get s1 is equal to 32 minus 28, which is 4. Good. So now, very similarly, we're going to find the x2 intercept for the second equation. So for the second equation, if these two are 0, then x2 has to be 84 divided by 4, which is 21. But again, in that scenario, we're letting x1 be 0 and s2 be 0. Okay, good. So that means, what does s1 have to be? Well, if x1 and x2 are 0 and 21 respectively, then in the first equation we'll get 0 plus, let's see, 2 times 21 is 42, plus s1 is equal to 32, So subtracting, we'll get S1 is equal to negative 10, which is also no good. Basically what this tells us is that we would not be in the feasible region, basically. So now one last thing to do. And the one last thing we need to do is we need to set S1 and S2 each equal to 0. Because when S1 and S2 are each equal to 0, we will have our system of equations that we saw before. It was that one corner point that took a little bit of work. So if you imagine that S1 and S2 aren't there, how can you solve this system? Well, in this case, if you multiply the top by negative 2, you get this. Bottom will stay the same. If you add straight down, you get x1 is equal to 20. I don't know why I keep writing 82. This should be 84. There we go, you get 20. And if you plug x1 equals 20 back into either of the equations where s1 and s2 are each 0, well, to find x2, I guess let's plug it into this. So if x is 20, x1 is 20, then that means we're going to get 2x2 is equal to 32 minus 20, subtracting it to the other side, dividing by 2, x2 would be 6. Perfect. So now what are we going to do? Well, now we're going to plug these x1 and x2 solutions. The only ones we care about are the ones in the feasible region, and we already marked off the ones that were not in the feasible region with this sad face, so I'll just cross it out now. And we're now going to plug them into P because we're trying to maximize P. So now we want to see which one will give us the largest value, and we'll just plug them in. And again, we're only considering the x1 and x2 values when plugging them into P, because P doesn't involve the slack variables. The slack variables only come into play when you turn the inequality system into an equality system. So let's see, when you plug in 0, 0 to P, you get 0. When you plug in 0 and 16 into P, you get 0, 16 times 80 is 1280. When you plug in 28 and 0 into P, you get 1400. And finally, when you plug in 20 and 6, you get, let's see, 1000, and then that is 480, so it's 1480. And of course, the one that corresponds to the maximum is the largest of these values. And that occurs at this point, 20,6. Just real quick, I want to go over some important notes here. The variables x1, x2, x3, and so on are called the decision variables, and we call the number of slack variables lowercase m. And let me just say that in a two-decision variable problem, like the one we just saw with x1 and x2 only, the number of columns in the table we created would be m plus 2. Of course, if you include p in your table, then you add 1 to that, so plus 1 if you're including p in the table. The number of rows in the table, though, is this quantity. It's m1, or m plus 1 times m plus 2 all over 2. And let me try to convince you of that. So in the problem we had, so just as an example, in the problem we had x1, x2, and we had two slack variables, s1 and s2. So notice this is indeed m plus 2, because since there are two slack variables, this means that m is equal to 2. Okay, so m was equal to 2, so the number of columns will be, well, 2 plus m, or m plus 2, which is 4. Which makes sense because we have only two variables and two slack variables, so adding those together gives us 4 columns. But then, if you remember the rows, how many rows were there? Well, we did x1 and x2 were 0, and then we had one of these each being non-zero twice, one for each equation. And then we had finally s1 and s2 were both 0. So first we had x1 was non-zero, something like this. And then x2 was non-zero, that was something like this. Then we had the same thing again, but in the other equation. So that would look something like this. So if x1 was 0, it would be 0, and then 0 for s2, because it's in the second equation, so s2 would be 0 to have x1 be non-zero only in the second equation. and then this would be 0 and 0 like that. And then finally it was 0, 0 for S1 and S2 for the last one, where we want to find that hard corner point that we have to solve the system for actually. Anyways, if you don't want to do this counting like I'm doing, because it's kind of hard to see maybe where my mind is, how many rows are there? Well, there's 1, 2, 3, 4, 5, 6 rows. There's a way to calculate how many rows that you need total just by doing this calculation. Since m is 2, the number of rows is just going to be, well, we use this formula here. So it's going to be 2 plus 1 times 2 plus 2 all over 2. So that's 3 times 4 over 2, that's 12 over 2, so that's 6. So we'll have 6 rows. So that's just a quick way to figure out how many rows you have, so you don't have to do this counting. But looking at the E system, you can kind of figure out which ones you want to be 0 and then just fill in the non-zero entries in the table. Alright, so this is the last example I want to do for this section, and it's basically the same problem, just different numbers, and let's see how it works. First off, notice this is indeed a standard maximization problem like we defined earlier. And what we're going to do is we're going to first create our E system. So what is our E system? Our E system is going to be, well, the constraints that are not the non-negative ones, so just those two up here. And we need to attach a slack variable to make this an equality for each one. That's going to be 3x1 plus 2x2 plus some slack variable s1 is equal to 21. x1 plus 5x2 plus another slack variable s2 is equal to 20. So I hope you can see at least how I got this. Now we're going to create our table. Okay, so we need a column for x1, a column for x2, and then a column for each of our slack variables, s1 and s2. And then finally a column for p that we'll establish after the fact. But first we want to get all of the entries sorted out. So how many rows will there be? Well, since m is 2, you'll get 6 just like we did in the previous calculation. There will be 6 rows. So 1, 2, 3, 4, 5, and 6. Perfect. So the first thing is, well, again, since we have these constraints here, the non-negative constraints, it's possible for x1 and x2, that should be x2, it's possible for x1 and x2 to each be 0. So we have 0, 0 here. Now I'm going to find when x1 and x2 are non-negative for the first equation in our E system. So that would mean if x1 is non-zero, then we want to make these two 0 in that equation. So x2 and s1 are going to be 0. Okay, I'm just going to fill out the zeros so we can follow that. Now if I want x2 to be non-zero, then I need x1 and s1 to be 0. There we go. And then finally, for the second one, well maybe not finally, but for the second equation now, if x1 is non-zero, then x2 and s2 will be 0. Similarly, if x2 is non-zero, then x1 and s2 will be 0. So if you take a look, what we're doing here is we're doing this. We're setting s1 being 0, and in each one at a time we have each of the x's being 0 for either of those two scenarios. Same thing here, when s2 is 0, there's two scenarios. One where it's 0 also with x2, and one where it's 0 also with x1. Okay, great. And the last scenario, finally, so now I can say finally, is when s2 and s1 are both 0, and that's when we have that actual system of equations that I was talking about earlier. So now let's see what's happening. So when we have these to be 0, this is basically what happens. When you plug in x1 and x2 to be 0, you get this. s1 is 21, s2 is 20. Perfect. What about when x2 and s1 are 0? When x2 and s1 are 0, then 3x1 is 21, divided by 3, x1 is 7. So what's s2 then? Well, s2, let's plug in. So x2 is 0, x1 is 7, so we're going to get 7 plus 0 plus s2 is equal to 20. Subtract 7, s2 is 13. Really, all we want are non-negative s values. That's the whole purpose of the slack variables. So if you don't want to take too much time in actually figuring out what s1 and s2 are, you don't have to. The only thing you need to assure yourself is that they're indeed positive, because the negative ones is where we start canceling out rows, if you remember that. So we'll see that soon enough. In fact, I think we're going to see it right now. When x1 and s1 are 0, then we get 2x2 is equal to 21. If 2x2 is equal to 21, let me write it here, then that means x2 is equal to 21 over 2. Now 20 divided by 2 is 10. 21 divided by 2 is 20, well, it's 10 and a half. So it's going to be 10.5. I'll just write that. So now, if x2 is 10.5, then here's what we're going to get. 5 times 10.5, x1 is 0. So let me just erase this. So we'll have 0 plus 5 times 10.5, well, 5 times 10 is going to be 50. So subtracting something a little bigger than 50 to the other side will give you a negative value for s2. So really we don't care what it is, but I'll tell you what it is. I'll just do the calculation myself. And let's see. 10.5 times 5 is going to be, I believe it's 5250 or 52.5. So with that being said, to solve for s2, you subtract that to the other side, and you'll get negative 32.5. And remember, this is bad. Because, since the slack variable is negative, that means that this solution is not in the feasible region. Good. Moving on, when x2 and s2 are 0, then x1 in the second equation is just going to be 20. And if x1 is 20, this would be 60. x2 is 0 in this case. So if this is 60 plus 0, so let me write that below. I'm just kind of using this area for my work here. So I get 3 times 20 is 60 plus 0 plus s1 is equal to 21. Subtract 60, you get a negative number. That's negative 39 in this case, and that is also not good because that means the solution x1 and x2 will, again, not be in the feasible region. I know it's a lot, but if you rewatch this and try to do the example on your own, you'll try to pick up on, you'll eventually pick up on what I'm doing here. So now, when x1 and s2 are 0, so let me erase this one now. When x1 and s2 are 0, we get 5x2 is equal to 20, divided by 5, x2 is 4. But what's s1? Well, if x2 is 4, we're going to get 0 plus 8, because 4 times 2 is 8, plus s1 is equal to 21. Subtract 8, we get 13. Perfect. And now, finally, when they're both 0, when both s1 and s2 are 0, we're going to ignore them completely, just like that, and we're going to solve that system. Now, the way I'm going to solve this system is by elimination. I'm going to multiply the bottom one by negative 3, and that'll cancel out the x1s. So what we get after doing that is 3x1 plus 2x2 is equal to 21 for the top equation, negative 3x1 minus 15x2 is equal to negative 60 for the second equation. Add straight down, the x1s cancel just like I said they would. We get negative 13x2 is equal to negative 39. Okay, divide by negative 13. Negative over negative is positive, so x2 is going to be positive. 39 over 13 is 3, so x2 is 3. What's x1? Well, if you plug x2 being 3 back into this, let me write it. I have some space, let me write it here. So we're going to get x1 plus x2 is 3, so that's going to be 3 times 5, it's 15, is equal to 20. Subtract 15, we'll get the x1 is equal to 5. Perfect. So now we're going to find our p-values for each of these that are not sad. So for each of the ones I didn't cancel out there. And again, when finding p is only dependent on x1 and x2. We've already dealt with the slack variables. The slack variables just help us determine what are the actual corner points in the feasible region without graphing it. And it may make you think, well, isn't graphing just easier? And the answer is yes, graphing is a lot easier. People don't like to graph for some reason, but let me just tell you, anytime you introduce graphing at all, that visual of allowing you to see what the solutions are just gives it a different dimension, and it actually does make it more efficient as it turns out. If you don't graph, you have to do stuff like this. There is a plus though, and we'll see that in 6.2 and 6.3. We can actually refine this this table method in certain situations to cut corners a little bit and make it a little faster. We'll see that in those videos though, that's okay. But in any event, let's continue. So when x1 and x2 are 0, we get p is 0. Okay. When x1 is 7 and x2 is 0, we get 70. When x1 is 0 and x2 is 4, we get 0 plus 100. And finally, when x1 is 5 and x2 is 3, we get 50 plus 75. 50 plus 75 is 125. And that's the largest one actually. So this is our maximum, and it occurs at this point, 5, 3. Whew, nice. So I hope we enjoyed 6.1. It was, like I said it would be, chapter 6 is going to even get worse, but try to rewatch this video a few times, try to do the problems on your own and compare, try to get a handle on this table method. It is only going to help reinforce knowledge for 6.2 and 6.3. I'll see you in the next videos. Thanks for watching.